Hey there and welcome to this video. I am Marius Momeu from TU Munich, and in the following I will present our paper titled IUBIK, where we propose a novel approach to mitigate memory safety vulnerabilities in commodity operating system kernels. IUBIK is joint work with Alexander Gaidis and Vasilis Kemerlis from Brown University and with Jasper von der Heid, also from TU Munich. We created IUBIK because despite decades of research, memory safety errors are still daunting commodity OS kernels. Nevertheless, analyzing existing exploits reveals a common exploitation pattern. First, attackers abuse a kernel object that stores user data, which they control, to cause type confusion with a kernel object that stores security-critical metadata, such as function or data pointers, allowing them to mount code reuse or data-oriented attacks. Second, to achieve this type confusion, attackers typically rely on so-called elastic objects whose size they can control to match the size of the objects targeted in type confusion. IUBIK mitigates this by leveraging ARM's memory tagging extension to isolate user data while stored in kernel memory, by rewriting kernel elastic objects to prevent type confusion, and by employing dynamic profiling to reveal various call sites that involve user data. The Linux kernel provides the functions copy from user and copy to user to kernel subsystems to interact with user space programs. Copy from user fetches data from user space, while copy to user sends data back to user space. The code listing on the slide shows how the add key syscall uses copy from user to process user data. The syscall first allocates a heap object of type user key payload at line 4, in which it then copies user data using copy from user at line 5. Interestingly, because attackers control the arguments passed to the syscall, they can also control the size of the heap allocation through the variable plen. This is what makes user key payload a so-called elastic object. Furthermore, if we look at the struct definition of user key payload, we see that it mixes user data stored in the flexible array field highlighted in red with object metadata such as the object's destructor at line 2. Now, these properties make elastic objects that mix user data and metadata very attractive for exploitation because attackers could abuse them to cause all sorts of type confusion scenarios. For example, if attackers targeted a security-critical object that's allocated in a kmalloc cache and victim of a use after free bug, they could massage the heap by allocating a series of user key payload objects by adjusting their size so that they are also allocated in the same kmalloc cache, allowing them to overlap the security critical object and manipulate their contents using the user-controlled data buffer. In Linux, these are known as same cache attacks. Similarly, if the two objects were allocated in different caches, attackers could now trick the underlying page allocator to reallocate the affected page where the security critical object was stored for a page that stores user key payload objects, allowing them now to cause type confusion again and manipulate the contents of the security critical object. In Linux, these are known as cross-cache attacks. And furthermore, attackers also leverage user-controlled objects to exploit heap overflows by massaging the heap allocator so that a user-controlled object that's the victim of a heap overflow is placed next to a security-critical object on the same memory page and use the overflow of the former to corrupt the contents of the latter. Now, these primitives in combination are so powerful that they could be abused to exploit almost any heap vulnerability in Linux. This is why in IUBIK we aim to mitigate all of them by segregating user data so that it cannot reach security-critical metadata. And we achieve this using ARM's memory tagging extension, which is a new hardware feature. With ARM MTE, each 16-byte memory granule in RAM is tagged with one of 16 tags, and memory access is permitted only using pointers that have the same tag. For example, in the figure on the slide, pointer 1 can access object 1 in RAM because they have the same tag, but not object 2. Using this mechanism, we design IUBIK to split the kernel's heap memory into isolation domains, which we call DOM-U and DOM-K. DOM-U stores user data on physical pages that are tagged with tag U, while DOM-K stores everything else on physical pages that are tagged with tag K. We facilitate kernel subsystems to allocate memory in DOM-U by maintaining a new set of kmalloc caches called kmalloc UBK, which can be accessed by passing a new memory allocation flag called GFP UBK to kmalloc invocations. Now, using this mechanism, we manually instrumented kmalloc sites that allocate user-controlled objects with the GFP UBK flag, effectively forcing them to reserve memory hosted in DOM-U, while the uninstrumented original kmalloc invocations will allocate memory in DOM-K. This effectively mitigates same cache attacks in UBK. Furthermore, because our isolation policy demands that physical pages hosted in DOM-U are tagged with tag U, while physical pages hosted in DOM-K are tagged with tag K, whenever we reallocate a physical page from one domain into the other, we also retag it, which mitigates cross-cache attacks because any dangling pointer that might have emerged while the physical page was used in the previous domain will be tagged with a different tag than the current physical page's tag. And this segregated architecture also neutralizes overflows from one domain into the other because, again, MTE will block accesses to pointers that don't have the same tag in hardware. Now, as we've seen earlier, some kernel objects mix user data with security critical metadata. So if we just allocated them in DOM-U, they could be targeted by the same type confusion scenarios presented earlier, which would allow attackers to corrupt these security critical fields. That's why in UBK, we rewrite such objects to decouple user-controlled fields from security critical ones. And in the case of user key payload, we first convert the flexible array into a pointer, and we adjust the add key syscall to use the new object layout. Specifically, at line 5, we modified the initial kmalloc invocation to reserve only a fixed size for the original object, which is going to be stored in DOM-K. And we add a new kmalloc invocation at line 6 that uses the GFP UBK flag to reserve memory in DOM-U, where user-controlled data will be stored. Finally, at line 12, we introduce a new k-free invocation to release the newly allocated memory for the segregated user buffer. Now, using this mechanism, we manually instrument and rewrite the kmalloc sites and struct types abused in existing exploits. However, we also wanted to reveal other potentially interesting struct types that could be abused by future exploits. And for that, we developed a dynamic profiling framework called the User Copy Profiler, which extends Linux's memory allocation profiling feature and is able to record alloc, user copy, memcopy, and free call sites that involve user data in Linux. We've generated a dataset for the User Copy Profiler by deploying a diverse suite of user space workloads, which includes both functional tests as well as performance benchmarks. And we've executed each workload twice, once as a privileged and once as an unprivileged user. And our results revealed 292 privileged and 212 unprivileged kmalloc sites that allocate user-controlled objects in Linux. Well, check out our paper to see other interesting findings and statistics regarding this experiment. Furthermore, we've evaluated UBK's performance by developing a prototype where we rewrote 79 alloxides and 23 objects that were recorded by the user copy profiler during boot, LMBench, and Phoronix. And we've deployed these performance benchmarks on a Pixel 8 that has support for MTE. And the table on the slide shows that UBK incurred its worst case performance on fstat and open-close, while almost no overhead at all in all the other benchmarks from LMBench. And on Phoronix, UBK incurred almost no overhead at all in all tests. In terms of memory overhead, we've measured UBK's maximum resident size set while booting the kernel on the Pixel 8 and computed that it requires 2.17% more memory than vanilla. We've evaluated UBK's security effectiveness by analyzing 31 recent exploits that target both use after freeze and heap overflows in Linux, and determined that UBK can mitigate 90% of them. Now check out our paper to see which exploits could not be mitigated by UBK. In conclusion, UBK proposes a novel memory isolation approach to mitigate memory safety errors in operating system kernels by leveraging ARM's memory tagging extension to isolate user data while stored in kernel memory, and it achieves this with negligible performance and memory overhead. UBK also provides a new memory allocation framework, a memory profiling framework that called the user copy profiler that is able to identify various call sites that involve user data. Now check out our paper to see more implementation details and interesting statistics from our evaluation. For example, we had to use ARM's pointer authentication to protect some pointers in some corner cases in UBK. Thank you for watching.